Welcome back, ladies and gentlemen. We're going to be looking at simple harmonic motion here, where basically an object is going to be oscillating, moving back and forth at regular intervals. And what makes it simple harmonic motion as opposed to a basic periodic motion is there's this restoring force, the force that acts to restore it toward equilibrium. And I'm going to be considering this idea of a mass on a spring. And we've taken the mass, and it would have been here, and we just pull it this way. So there's this location where it was at equilibrium. And we have equilibrium. We've displaced it from equilibrium a certain distance, right? So I'm going to mark that distance here. And we'll call that A for amplitude. That's how far it's moved. And at this location, it's not moving, and I would release it. And what's going to happen is there is a restoring force, the force in the spring. It's going to pull it back toward equilibrium. And it's going to shoot past this location because it's got a lot of momentum now and kinetic energy. But then as it swings this way, the spring is going to be exerting a restoring force that way now. And it would swing back, assuming there's no loss of energy due to any other influence. It's going to swing back, or it's going to kind of overshoot equilibrium and head this far. And get that far, which is also equal to A, the same amplitude away from equilibrium. And that's the idea. And it would just kind of oscillate back and forth between amplitude down this way and amplitude this way. So want to make sure I'm clear on a couple things. Number one, let's have that way be in the positive direction. Okay, fair enough. There's a couple other things. There's this idea that there is a period of oscillation. The time it takes to complete one oscillation, that'll be measured in seconds, right? Time for one oscillation. There's also this idea of frequency. And I'll use the symbol lowercase f, sort of fancified like that. Frequency is going to be the number of oscillations that a system goes through in 1 second. Number of oscillations per second. And the units here will be called hertz, named after this guy. And so the hertz, 1 hertz, is the same as 1 cycle or 1 oscillation per second. So there really aren't any units up here. It's just 1 trip there and back every second. That's 1 hertz. The interesting thing is, if you look at the definitions of period and of frequency, you realize that they are inverses of each other. And that's an important relationship to remember. I'll put a box around that for you. So anytime you know one, you really do know the other if you simply take the inverse. So now what we want to do is we want to be able to describe this motion. Mathematically, we're going to try to figure out what we could say. Could we describe the position of this object at various times? Could we describe its velocity at various times? Could we describe its acceleration that it's experiencing at various times? And the answer is, of course, we can. So I'll bring that diagram back from time to time. But essentially here first, let's look at how we can describe the position of that oscillating mass. We're using this mass on a spring. So what's the deal here? Okay, I'm going to look at the position versus time, and just call it position X if you like. We can say that this positive direction is the positive X direction, that way, and that's cool. And by extension, there will be a negative x direction this way, and there will be some positions that are negative direction, right? Now, what do we know? I've pulled this mass to this maximum position in the positive direction, and I'm going to let it go. And so when I let it go, there's some other things I understand. For example, I've pulled to this maximum position A, and that's where we start. And it's initially not moving, so there's no velocity here. And so how do I represent no velocity on a position time graph? That's essentially what we have here. No velocity would be zero slope at that location. And at some point, it's going to get to the zero position, the equilibrium position, right? But it will have spent all this time getting there, accelerating because of that restoring force of the spring. So once it gets here, it's really at its maximum velocity. As it goes past and overshoots it, it's not speeding up anymore, because now, even though movement is this way, the restoring force is in the opposite direction, and it will be slowing down once it passes this position. And so I know that at that equilibrium position, it has maximum velocity. And so I want maximum slope here. But notice that when I let go, its velocity is in the negative x direction. So I need a steep negative slope here at position 0. So a steep negative slope. I'm going to end up connecting things in just a moment. Then at some point it's going to reach a new position, which is A in the other direction. Really, that's going to be a negative A, right? And at that location, it's got no velocity. It stops for just an instant. So again, we're going to be at a new position, negative A. And at that new position, we're going to have a slope of 0, no velocity. And this pattern keeps repeating. And you're going to notice right away, at least I hope you do, that we're going to be creating this sort of pattern. We're going to have that. And you should start to recognize this right away as a particular function, right? And it will keep going. It will continue. So I'll just do one more little thing there. And so here's the deal. Here is the actual relationship. I can make a couple notes here. Remember that there is velocity of 0 at that location, so we had that 0 slope. Here we had moving fastest. And so on. So we can see it's moving fastest here also, just in the positive direction, because we have a positive slope right there. Here we had a negative slope. And now, we can recognize that this is going to be a cosine function, right? So our equation for the position, we're going to have the amplitude times the cosine of this business in here. And this is essentially going to be something related to time here. Well, let's look at what's happening with time. We have, for one complete oscillation, it's got to come down and back up and get back to its starting position, right? So at that moment, it has gone through one complete oscillation. So that time would be the period. And this is another connection, another place where we see a connection between simple harmonic motion and circular motion, because we now have this 2 pi divided by the period inside this term, and that's multiplied by whatever time we're at. So what is our position going to be? However much time goes by, we're going to multiply the time by this relationship, take the cosine of that, multiply by the amplitude. Okay, so what is this going to mean for us? Check this out. When the time equals capital T period, well, what does this sort of turn into? When t equals capital T, it looks like they're going to cancel out, and we're going to be taking the cosine of 2 pi. Well, the cosine of 2 pi is just 1. What about when the time is twice the period? So it's gone through one complete cycle and then a second complete cycle. Then you're taking the cosine of 4 pi. And that's still 1, isn't it? It's just twice the value of that. So it actually doesn't matter as long as the time you're looking at is some integer number of the period. Then you're going to have the cosine of basically n times 2 pi, aren't you? And that's whatever n is, it doesn't matter, it's still going to be a value of 1. And so this is interesting. So when that's the case, what we see is that it's back at maximum position, right? There is a way we can describe the maximum position. And so we know cosine of 1 is, or I'm sorry, cosine of any of these values is going to be 1, and so the maximum position is just A. That's something interesting we can say from this. Also, look at what's going on here in parentheses. We see this 2 pi divided by the period. Well, that by itself is something interesting. That right there is how we're going to define this weird triple equal sign. It means we're defining something. We're defining this thing that looks like an angular velocity. We're going to give it a new name and call it angular frequency. Not just frequency, not just f, but angular frequency. It pretty much is the same as your angular velocity. So our units are still going to be radians per second. But that's going to be kind of handy. What I'm going to be able to do is make a substitution for 2 pi over t for this. I can write that omega in there. This is an important equation. You want to remember it. But what you're going to start to realize is, as we go through the next couple of things, all we're really doing is coming up with kinematics equations for this oscillating business, for the objects experiencing simple harmonic motion. So where is it, how fast is it going, and how fast is it accelerating, right? Just like we did with rotational stuff, and just like we did a long time ago with linear stuff. So this is nice. This is looking pretty good so far. We can handle this. The next step, of course, we looked at position. The next step was going to be velocity. Let's check that out. Trying to keep the pace moving for you guys here. So, how can we describe the velocity of this mass on the spring? Well, I have to be able to look at this guy. And the reason is, recall again that velocity is simply the slope of a position-time graph. This is one way to think of this. So I'm going to create a new graph here. This will just be a velocity-time graph. And initially, maybe I shouldn't say initially, there's definitely some important points here. I'm lining these two up on purpose. And the purpose is that one period is still just one period. And there's some interesting things. We have at a position of 0, it's going really fast. And at a position that's maximum, it's going not at all. It's got a velocity of 0. So we can tie a few things together. At this point, there's something important going on. And at this point, there's something important going on, right? So what is all this going to mean? Well, okay. There's 0 velocity. Now, I have 0 velocity at maximum amplitude, so right here, velocity would be 0. I've got a data point right there. And then here, I've got the maximum negative velocity. So whatever this is going to be, I've got maximum negative right there. And then down here, I've got 0 velocity. And then here I've got maximum positive velocity, so I'll have a positive velocity max up there. And then I've got, again, a velocity of 0. Slope of 0 on the position time graph gives me a velocity of 0. So this is pretty slick. So I can check out a pattern here, and this also should look real familiar to you. Sure looks like a sine graph, a sine wave, but it's been inverted, right? So there's some things we can discern from that as well. Also, if you understand some calculus, and I should note this, if you understand some calculus and you take the derivative with respect to time of this, then you're going to end up with the equation that we'll show here. So remember, for position, we had the position equals amplitude times cosine of angular frequency times time. Well, velocity now, how can we describe the velocity? It's going to be the negative of amplitude times angular frequency here times the sine of that. Okay, and if calculus isn't your thing, or if you're not there yet, don't worry about how we get from there to there. You just trust that this is what we have going on. So think about this. We have a sine wave, and it's the inverse of it, so it's just flipped. A normal sine wave would go up first and then down, but now we're heading down first and then up. That's why you have this negative sign. And so this is also an important equation you're going to want to remember. But where does the maximum velocity occur? This should be pretty easy to say. Maximum velocity is going to be at these 2 points here and here. For example, that guy. And what is that? Well, just like maximum position was where everything here was equated to 1, maximum velocity is going to be where everything here is equated to 1. And essentially, that's going to be equal to that. And down here, negative amplitude times angular frequency. So, there we go. That is our maximum velocity, is whatever this value would end up being for a particular system. Now, what about acceleration? So, recall that acceleration can be seen on a VT graph, as the slope of that graph. So we're going to set that up, and I'm going to want to be able to see this graph now. Not very straight on that line, but you get the idea. So now this is an acceleration time graph, and this is kind of weird. We never really dealt with acceleration time graphs very much, but it's worth doing here. We'll have an acceleration of 0. We'll have some maximum and some minimum value of acceleration, and so the slope of the velocity time graph. Where is the slope greatest? It's here at 0. It's greatest here at this midway location, and it's also greatest here at the end of one complete cycle. Remember, this is still one cycle. That's the period t, is that amount of time. Well, I should probably make sure these are lined up, and I should continue to do this, and that, and a little bit of just making sure that gets lined up, and then this guy. Okay, I think we're good at this point. So now, maximum slope here, well, that's a negative slope right here, and so maximum negative slope, I have a data point right there. And then 0 slope, I'm back up at 0, and then maximum positive slope here, back to zero slope there, and maximum negative slope one more time here, maximum negative slope. Okay, so you might think, oh, sure, just kind of inverted parabola there. No, you got to be real careful. We're looking at this kind of pattern. There you go. So, you know, that should look real familiar. If I were to turn it this way, you'd say, oh, that looks like a cosine function. So what we have is an inverted cosine. And that's exactly it. We have, for acceleration of the mass on the spring, we have an inverted cosine function, so there's going to be a cosine here. But I have to put this out front. So there's amplitude times angular frequency squared, cosine of angular frequency times time. That's the equation for the acceleration of this mass on the spring. That's an important thing to remember as well. If you're into the calculus or trying to figure that out, basically take the derivative with respect to time of this business and you end up with this. If calculus isn't your thing, that's okay. Trust that this is what you need to do, or this is what you need to use. So where is the maximum acceleration taking place? All right. Well, it's going to be where cosine of this is equal to 1. And so that's going to be wherever we have this value. And so I should mark these here. There and negative there. Okay. So if you wanted to know the greatest amount of acceleration, it would be wherever this whole cosine term of the equation goes to 1. And we're going to see maximum acceleration at half the period, at full period, and so on. All right. So now we've got some basics that we can use to describe what's going on here. Want to bring back the diagram that we saw originally, the diagram of our physical situation. So essentially we had fixed position, fixed location, the mass on the spring. And we had displaced it or disturbed it, amplitude there and negative amplitude there. This position would be equilibrium. And it's oscillating back and forth. Well, when it's over here at A, there is a force. Of course there's a force. It's a restoring force. It's a force in the spring. Here, at equilibrium, it's not stretching or compressing the spring at all. So the force in the spring is 0. Over here, at this location, the restoring force would be that way. It will be maximum. That kind of makes sense. So check this out. Where the maximum force is, you would expect maximum acceleration. Maximum acceleration takes place at either end mark, right? Okay. Well, what about this force in the spring? If you recall your spring information, you've got force of a spring is equal to negative kx. X is the amount of stretch or compression, the displacement of the end of the spring. And k is just the spring constant. All right, cool. When all other forces on the object are balanced, then the spring force can be thought of as the net force. And that's neat because what I can do is I can say, well, now it's the net force equal to negative kx. Well, net force is mass times acceleration. And here we have negative kx. You know what's coming next, right? We're going to do a couple substitutions. The acceleration. I'm going to plug in this business for the acceleration of that mass. And for position, I'm going to plug in this business for position into this equation. So, rewriting this with those substitutions, I'm going to give myself more room here. We have mass. and the acceleration is negative amplitude, angular frequency squared, times cosine of angular frequency times time. This is all multiplication going on there. And now, negative k and position. Position is amplitude times cosine of angular frequency times time. All right, cool. We're definitely getting somewhere with this. I can see I got a bunch of stuff canceling out. Watch this. Cosine of angular frequency times time is on both sides. It goes away. Amplitude is on both sides. It goes away. There's a negative sign on both sides. Negative sign goes away. And what am I left with? I'm left with spring constant. I'm left with angular frequency squared, and I'm left with mass. Okay. So this is going to be k divided by m. Now, what about, okay, one more step, I'm sorry. Here we go. Let's take the square root of both sides. K over m. Radical k over m is that angular frequency. Okay, this is real trick right here. Real important. I'm going to put a box around that equation. Not just because it is important, but the next step is also important. That's the equation for the angular frequency of this oscillating mass on the spring. That's it. You need to know the spring constant, you need to know the mass, and from just those two numbers you can get that angular frequency. But there's more. Of course there is. This is angular frequency. Well, there's a couple things I want you to recall. Let me start a new paper. This is just too good. So, recall that frequency is 1 over the period, which means the period is 1 over the frequency, right? But also, I want you to recall this. When we're dealing with these things, this is super important and so useful. Look at this. This relationship right here where we can take this and substitute in essentially either one of these, depending on which one you think you might need. But I'm going to do one in particular. I'm going to take this and rearrange it for the period. It is simply 2 pi over omega. And now I know that omega is radical k over m. So now this is usually not how it's expressed or viewed. It's kind of clunky to have the radical in the denominator like that. It would usually be rewritten to look a little slicker. So you got 2 pi. And how do you get rid of this in the denominator? Well, you take the inverse. You invert it. So essentially that. All I did was I inverted that fraction and this all works out. So check this out. There's one more hugely important thing going on right here. This is big, and the previous 3 equations for position, velocity, and the position, velocity, and acceleration are also big, right? You know what you have here? You have an equation for the period of the mass on the spring. 2 pi times radical mass over spring constant. Wow. Okay, so good. Good stuff. Thank you for watching. I'll catch you next time.